Okay, everyone. How y'all doing?
Doing okay?
All right. So let's talk about where we're at, what we're doing. So today we're going to do improper integrals, chapter 6, section 6. This section is broken up into two parts. The first part is called improper integrals dealing with infinite intervals. And then the second part is called improper integrals dealing with infinite integrands. Today's material will be on exam 2. The material we cover on Monday will not be on exam 2. Exam 2 is next Wednesday, which is the last day before spring break, right? And I just sent an email with the review for exam 2. But I did say in that email to not limit yourself to just those problems. Here's the actual review that I just sent out. It just gives you some indication of some of the things I've asked for in the past. And on this particular review that I sent out, you need to throw out number 5, because number 5 has to do with what we're going to do on Monday. This is an improper integral where you have an infinite integrand. So again, we'll cover that Monday, but it's not on the test. So on this review, just ignore number 5. But you can see I only asked 6 questions on this test because they take a while, right? The problems take a while. So yeah. Let's get going. Are there any questions before I begin? Can't hear you, Brandon. Can't hear you. Just chime in again whenever you get it fixed. Okay, so we're going to talk about improper integrals on type 1 improper integrals, which are called infinite intervals. So up to this point, really from last class, we were talking about looking at the area under a curve on some interval A to B, right? But it was always like from one number to the next. And those were the numbers you put into your on your integral sign, and that's what you plugged in at the end using the fundamental theorem of calculus. Hopefully you're able to go and do some of your old homework and just plug numbers in and get some numerical answers. We're now going to investigate areas on infinite intervals. So instead of going between 2 points where we have a closed interval, we want this interval to be infinite, meaning it goes forever in one direction, or it goes forever in both directions. So that's what the task is right now. Question in the chat: will the test be 6 questions, or I haven't made the test, so I can't tell you how many questions it's going to be. It's more going to be about me trying to make a test that I think that you can complete in the 100 minutes that you have to take the test. So it could be, 5 questions, 6 questions, 7 questions. I wouldn't expect it to go over like 8. But remember, you come in, we have to get everything set up. So the faster you get into the Zoom session, get set up and get your camera right, the less time we have to wait and waste, right? So you're going to be counting on your classmates a little bit to get their stuff in order. So we've had 1 exam already, so hopefully the second exam will be smooth. All right, so when we're looking at these integrals, improper integrals, this is the way that the integral notation is going to look. It's going to be different than what we've seen before. So instead of going from A to B, it might be A to infinity, or it might be negative infinity to B, or it could be negative infinity to infinity, which negative infinity to infinity means, you want the area under some graph in both directions forever. So you might be thinking to yourself, like, okay, well, is it even possible to get an answer here? Because if you're talking about the area under a curve where it goes forever in one direction, that might leads you to believe, well, you're just going to have an infinite amount of area because you're always adding more and more area and you keep going in one direction. Well, it turns out that that's not the case. Sometimes the area is finite and sometimes it is infinite. It just depends on the actual function we're looking at. So
would a sine wave's area end up being 0?
no, a sine waves are in one direction only, right? You're saying that, or in both directions?
From infinity, both directions. Wouldn't it
Both
end up
directions.
being 0 under the curve?
We would say that that integral, right? That integral diverges. Now I'm going to get to that. I'm going to define everything here in a second. Hopefully it'll make sense after I define everything. All right.
Yep. All right.
I can understand how you would think it's 0 because everything's going to like cancel everything out, but because of the way we define the improper integral, our answer for that's going to be diverges. So here's the way it works, okay? If you're trying to do the integral, the area underneath some function, and you want to go from some a here forever to infinity, the notation is this, right? That's the notation I just introduced to you. But what does the actual notation mean? The notation means that you're going to do a normal definite integral like we did last class, and you're going to go from a to t. So you're going to replace the infinity with t. You're going to figure out what the answer is here using the fundamental theorem of calculus. When you do that, since a is a number and t is a new variable, your answer from this will have t's in it, right? It'll be just some expression that has t's in it. And then what you're going to do is you're going to take the limit as t goes to infinity. You're going to let that t go to infinity after you've done the actual when you've actually done the definite integral. And that answer will be your answer to what the area is. Now, because limits are a little bit sensitive to certain situations, sometimes limits exist and sometimes limits don't exist, right? And if the limit does not exist, then we're going to say something. And if the limit does exist, you're going to get some numerical answer. So let me continue with the notes here. If you want to do this situation where you want to go from negative infinity to b, that means you have some point b here and negative infinity is out there, and you're trying to find all this area underneath this curve. It's the same situation. You're going to leave b as b. You're going to replace negative infinity with t. You're going to figure out what this is using what we did last class. And at the end, you will take the limit as t goes to negative infinity. If that limit exists, then you're going to have an answer. If it doesn't exist, then, well, what do we do? Well, here's the next part of the note. If these limits exist, we will say that the integral is convergent. All right. So if you do that limit at the end, you get a number like 4, then we will say the integral converges to 4. If the limit does not exist, we will say that the integral is divergent. And divergence just means non-convergence. Okay, so let me say that again, because this is a very subtle but important point. If we do this and we do a limit and we get an answer of 4, then what we're saying is that area is getting closer and closer and closer to 4. The further and further out you go, the closer and closer it gets to 4, and it never goes over 4. Divergence does not mean that it becomes an infinite area. It could be infinite, but divergence means not convergence. So you can have oscillation, you could have it going to infinity, but that's not important to us. What's important to us is that it's not convergent, therefore divergent.
Like it could go over a number and we just don't know like where it's going, basically. Is that
it could go over, well, if it goes over some number but never gets past some other number, then it would be convergent.
Yeah. So what I mean is like there's no set number, it's approaching. So there's no way we could tell If there's, okay.
That's right. There's no set number that it's approaching. Exactly. So like Hunter, in your
Or it's a
example
sine
with
wave.
sine, it's like you go out, right? And at some point, yes, you would have an area of 0 because they would offset each other. But if you go a little bit further, now you don't have the offset anymore. But if you go a little further, you might get 0 again. Then, but the thing is, it's not going to exactly one value. It's divergent. It's not converging.
Yeah, it's not actually approaching anything. It's bouncing up and down between 1 and -1.
But I guess
The area keeps changing as you go out, as opposed to going to some finite number.
Gotcha.
Okay, and now finally, we have the last situation, which would be where you go from negative infinity to positive infinity. Okay, so if you go from negative infinity to positive infinity, the way we're going to do this is we're going to split it up into 2 integrals. We're first going to go from negative infinity to a, and then add to that the integral going from a to infinity. Now, that was a property that we had last time, that if you ever want to find the area under a curve between a and b, you can always split it into 2 areas. This is exactly what we're doing here. We're going to split it into two different areas. Now, the a that you pick can be anywhere. So like you could pick an a right here. And what we're saying is we're going to figure out the area of this region here. And then we're going to figure out the area of this region there to the right forever. That's what this is saying.
Okay, sorry, sir.
Yeah.
I was gonna ask, the thing that we did last time when we split them up, we were subtracting, right? Or no?
No, it was, let me see, hold on.
Maybe I'm thinking of something else. Oh, I was thinking of like a and b, on the integral, not not infinity. Okay.
Yeah, I'll just show you the property here. Where was it? This one right here. This property said that if you want to find the area between A and B, that you can always pick any value in the middle of them, C, and then do the 2 areas separately and add them together. So go from A to C, then go from C to B, and that would be the same as going from A to B.
Oh, okay.
Okay, that's the property I'm referring to here. So we're going to go from negative infinity to any number A, and then continue from A to positive infinity. Now, what do you think the most convenient number for A is for us to use?
0.
0, right? Just right in the middle. Now, you don't have to use 0. You could use any number, but 0 is the one we usually use.
Unless we've got a variable on the denominator.
Yeah, unless we have a problem at 0. We have like a discontinuity or something, which is the second part of this section. Okay, the second part of this section is what if somewhere on the number line we have a discontinuity, like a vertical asymptote. That's Monday. We'll do that Monday. All right.
So I bet that tangent function is really exciting with this, because it's just made of asymptotes.
Interesting because there's all sorts of things happening with tangent with vertical asymptotes. Okay, so let's do our first example. We want to find the area under this curve. 1 over x squared is our function. We want to look at the area from 1 to positive infinity.
Professor, I have a question real quick.
Yes.
So I don't know if I'm seeing this right, but what's the difference between just saying like, oh, we're just going to insert our limit, like afterwards, after we integrate, put our variables in, and then put our limit inside? Like, is that the thought process I should be thinking? Or
here's the way I guess you can think about this. Look at this function 1 over x. Just let's look at this one specifically because I think it might help. I'm gonna go graph it. I have this ready to go here. All right, there we go. There's the graph of 1 over x squared. Okay, this 1 over x squared, but I'm only graphing it from 1. Notice I'm only going from 1 out to infinity, right? Forever. So we want this area underneath this curve, all that area forever to the right. Understand? The idea of doing this, we're doing the integral from 1 to infinity of 1 over x squared dx. The idea is that we're going to change this to a limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. This concept is this. Instead of going to infinity, we're going to stop it at t. And we're going to try and find out what the area of this is out to t. That's what this would be, right? That would be the area out to t. And then once we figure out what that is, we're going to let t go to infinity, which will take this point and drag it out forever. And once you drag it out, then you'll be accumulating the area as you go to the right by letting t go to infinity. Does that make sense, Lewis? Does that answer your question?
Oh, that makes perfect sense.
Okay,
Nice.
good. Everyone follow that? All right, let's go. Let's get to the work, okay? All right, so first thing I'm going to do, I'm going to realize that this is an improper integral, right? That I have an infinite interval because I'm going from 1 to infinity. So I'm going to automatically convert this into a limit as t goes to infinity. I'm going to replace the upper limit of integration, infinity. I'm going to replace that with t. And then I'm going to do 1 over x squared dx. Now, from what we learned last class, when we do a definite integral, what we first have to do is find the actual antiderivative of that, right? So what is the antiderivative of that? Remember, that's the same as x to the -2, right? So the antiderivative of that, I would expect everyone in here could get. It is -1 over x squared. I'm sorry, -1 over x. Right, add 1 to the exponent. You have to put a -1 over -1 out front. Do I need to go through that, or are we good?
No, I got it.
We're good. Okay, so that's the antiderivative, right? And then we put the evaluation bar, and we put 1 on the bottom and t on the top, like that. That is the beginning of us using the fundamental theorem of calculus, right? We are just going to take the antiderivative of it and evaluate it at these two endpoints. This leads me to this limit t goes to infinity. And then now let's actually plug in. So remember, when I was doing the plugging in, what I was doing was 2 sets of parentheses with subtraction between them. And I first put the top one in, right? So t goes in here first. So -1 over t. And then I plug in the 1, I get -1 over 1. And so now I have this limit t goes to infinity. And then this becomes -1 over t. And then this is a -1, but then I'm subtracting, so just +1. Now we let t go to infinity, right? We have an expression, this expression right here, right? This is an expression that has t's in it, right? So I'm going to take the limit now, and I'm going to let t go to infinity. And I hope everybody in here from Cal 1 knows what happens now, right? If you have -1 on top and the bottom gets huge, this thing vanishes and
this will
heads
just
to
become
0, right? That goes to 0. And that means the only thing left is +1. So your answer is 1, which means this integral converges to 1.
So I'm sure we learned this in Cal 1, but can you remind me what exactly you just did there?
I said to myself, I have a fraction where the numerator is not changing at all, right? -1.
Uh-huh.
And the denominator is headed to infinity. So
Right.
if you have a number on top that's fixed and you have a number on the bottom that gets huge, that ratio will get infinitesimally small.
Ah, gotcha. Thank you.
Okay. Now look, if that, for everybody here, if that concept is still a little gray, we're about to go into problems where we need L'Hopital's rule and all these other things from Cal 1. So we were gonna hit some road bumps here because not everybody, well, I don't know, we'll see. Let me do a quick poll. When I say L'Hopital's rule, did you do L'Hopital's rule in Cal 1? Yes or no? Do you remember doing it? L'Hopital, it's spelled like this. It's spelled like La Hospital. L'Hopital's rule.
Sir, I have a question.
You may not remember any of it, but yeah. Okay, Brandon, what's your question?
Okay, first question. Can you hear me?
Yes, I can now. Yeah,
Okay,
it's a little,
Second
little,
question. So if it was infinity plus one, then it'd be divergent.
that's right.
right?
Mhm.
Okay. So if
Yeah.
anything but a number, it diverges. Okay.
Yeah,
Okay.
yeah, let's say that this would have come out to be t plus one, okay, instead t plus one, instead of negative one over t. What if it was t plus one? Well, if we let t go to infinity, this thing goes to infinity, and therefore this would be divergent. Or we would say the integral diverges.
If I remember correctly, my limit rules, since it's in a limit, wouldn't if t was approaching 0, we end up with infinity plus 1 again?
If t was going to 0, negative 1 over 0 would become, well, actually
would-
that limit doesn't exist because from one side it's positive infinity, the other side it's negative infinity. The limit wouldn't exist, and therefore this would be divergent. But
Yeah.
we're never going to be going to 0
Yeah.
with improper integrals.
Yeah,
Like,
I-
I'm sorry, hold on, let me take that back. We're never going to be going to 0. T's never going to be going to 0 with improper integrals on infinite intervals. On Monday, we will be going to potentially 0. And yeah, we'll have to deal with that when we get to it.
Okay. I was just trying to remember how the more rules for the limits were working.
Yeah. So I think you're going to see today that we're going to need to understand the limit rules, and I'm going to try and refresh you as we go. From the vote here, 13 out of 17 said that they remember doing some L'Hopital. I've got 4 people that don't remember L'Hopital. For those 4 people, if it's that you never saw it, then you need to get with me, because the idea of L'Hopital's rule is something that we spend at least a week on in Cal 1, and there's a lot to it. I mean, there's a lot of little things that you need to know. And if you've never seen it and you're going to watch me do it today, you're gonna be like, what the, you're going to be, what is going on? So you're going to need to get with me, and I can at least point you to my Cal 1 videos, at least, where I cover those in a lecture where I actually go through L'Hopital's rule. But you need to reach out for help. All right. Which is why we cover it. I know there are some Cal 1s that they don't do L'Hopital, and I can't tell you for the life of me why they don't. But all right. Convergent.
Is that,
So-
oh, I'm sorry. I just,
No, go ahead.
was L'Hopital's where they multiply by the conjugate, or was that something else?
L'Hopital is where you take the derivative of top and bottom when you're taking a limit.
Oh, yes. Okay, thank you.
But that's not all. I mean, it depends on what form you have. If you have infinity over infinity, you do derivative top and bottom. But if you have like 1 to the infinity, then you have to bring in a natural log. I mean, there's a lot. There's a lot. Okay.
Okay, gotcha. Thank you.
We'll kind of like, let's cross that bridge when we get to it with these problems. And I'll point it out when I'm using L'Hopital. I'll let everyone know what I'm doing. Okay, visually, let's just take a look again at what's happening here. Here was the graph, okay? Here was the graph of 1 over x squared from 1 to infinity. I have the computer right now calculating right here the area. And let me add one more point here so you can see what I'm doing. Sorry, I didn't have a whole lot of time to put this together today. I was just kind of like last second thought I could do this. Okay, so what I'm going to do here is I'm going to drag this point. See the point? Oh, gosh, that's dragging very fast. So I'm dragging this point to the right. So what's actually happening here is the computer is adding up this area all the way to this point right here. Okay, and it's giving me the numerical value right there. Okay, so right now, if I stop right here, the area is 0.615. Now I'm going to keep dragging this to the right and just watch what happens. 0.94. Okay, I'm off screen, so let me shrink this down. I'm going to make this really small and make it like that. I'm going to go out to 100. So if I start dragging this to the right, just keep your eye on that number there. 0.97, 0.98, 0.9. Okay. 0.99. Let me go further. Well, I'm at 0.999. I've gone out to 1,000. All right. I'll go out to 1,000,000. If I go out to a million, it's 0.999999, right? And the further I go, the closer and closer I get to 1. Okay. If I ever stop anywhere, if I stop at a billion, that area will be just slightly smaller than 1. If I could theoretically go forever, it would get closer and closer and closer and closer to 1. Does that make sense? It's a weird idea, but that's what's happening here. Convergent area. All right, let's do another one. Let me back this thing up. Where's my M? I want to change this back to, let me change it back to 100. And back it up. I
So
should
as
have
an
it where it's actually shading as I go, but I'll do that another time.
So as an engineer, like we knowing that information, we can like know what not to go up to, or know like, okay, the area is actually 1.
I'm not quite sure I understand the question.
No, that's okay. It's just more like a spitball
Okay,
question.
what's a real life example of using
What's that?
this? Real life example.
So remember last time I was talking about probability density functions at the end of class? And I was talking about when you have these, when you have these continuous random variables, like the probability of, when you have like, you know, how tall is somebody, or how much does someone weigh? When you think about that, you can assign, you know, there's going to be like an average value. There's a probability that somebody, you know, weighs a certain amount, right? And then as you go to the left, let's say the probability drops down, eventually you get to 0 pounds. And of course, the probability of being 0 pounds and being alive is 0. But as you go to the right, what happens is that the probability keeps dropping down and down and down and down, right? Now, could somebody weigh 300 pounds? Yes, but it would be a very small probability, right? Like not very small, but small, right? Could they weigh 400 pounds? Smaller probability, right? 500 pounds, smaller probability. 600 pounds, smaller. How about 1,000 pounds? Can somebody weigh 1,000 pounds? You can't say no. You can't say no. Okay, this is the thing. You can't say no. You can say what? It's very unlikely, right? Very, very small probability. Can somebody weigh 10,000 pounds? You're going to say no, but I'm going to tell you that there is a probability that it could happen. But the probabilities we're talking about are infinitesimal. It's like this. What's the probability I win the lottery tonight? If I play the lottery, what's the probability I win? Pretty small, right? Pretty small.
Yeah,
Could it
almost
happen?
non-existent.
Could it happen?
Yes.
Okay. Could I play the lottery tonight, win, and then go play it again tomorrow and win?
Yeah.
Don't tell me no, Lewis. I could win twice in a row, right? You can't say no, right? You can't say no. The probability of me winning the lottery back to back, there is a chance. It's like that movie. What's that movie? Dumb and Dumber. Is it Dumb and Dumber where Jim Carrey's like, so you're telling me there's a chance, right? There is a chance that you could win the lottery twice in a row.
I have a question.
Yeah.
So Professor, what's the probability that you went biking last week?
Last week, I don't know if I did. Well, you know what? You cannot talk about probabilities for events that have already occurred. So like if I flip a coin, right? If I flip a coin and it lands in my hand, and I say, what's the probability that's heads or tails? That makes no sense. Probabilities are only for events that haven't occurred. The coin has already been flipped. It's already, the result is the result.
So what's the probability you'll go this week?
Pretty low. I've found that I'm getting more done when I work out at home. I've got a different routine going, and it's actually, it's better for me because my body is so good at biking. It's too efficient. I don't burn enough calories. So I burn more calories doing other exercises. Anyway, so very low. Okay, let me get back to this. The probability of me winning the lottery 2 days in a row is infinitesimally small, right? What's the probability that I play the lottery for 30 days in a row and I win every day for 30 days. I mean, we're talking, you know, we're
Virtually
talking
non-existent.
virtually non-existent, but there is some positive probability that it could happen, right? You cannot tell me it's zero, but it's infinitesimal.
But
Right.
if we for instance made like a graph on that, and
Yeah.
let's say that we graphed that possibility, wouldn't it be like an outlier, I'm guessing?
Oh, yeah, absolutely. I mean, it would look like this though, wouldn't it? Like the probability of me winning, this isn't really good, accurate representation, but the idea is here the same, right? Is that as we go to the right, the probability continues to drop, right? I mean, it is infinitesimally small, but it's there. And the further to the right you go, the smaller this graph gets, the closer it's asymptotic, right? The graph is asymptotically approaching zero, but it never gets to zero. So you're always going to have some area out there. The amazing thing is that the area, the total area though, from 1 to infinity never goes over 1. It converges to 1. And since the total area converges to 1, you could use this function as a probability density function because the sum of all probabilities has to be 1. Why? Because the sum of all probabilities means if you tell me what the probability of all the possible events are, it better be 100%. Right? There better be 100% chance that every outcome is possible. Does that make sense? It's like if you roll a die, there's 6 options. The probability of getting a 1 is 1/6, a 2, 1/6, a 3, 1/6. But what's the probability of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6? Those are the only outcomes. 100%, right? 1/6 plus 1/6 plus 1/6 plus 1/6, 6 times, that's 1. So I'm just trying to give you, like in real life, we really like functions that the area under them is 1, because then we can assign that to some sort of real life model where there's probability of something happening. You can even take this like engineering, you can take it to like probability that, we'll keep it simple. The probability that your phone battery is going to work, right? So like what happens, right? You buy a phone, man, it stays charged for like a full 2 days, it's all badass. And then like a month later, it's not as good. And then like a year later, right, you're plugging in at, 8 p.m. And then like 4 years later, you got to charge it like, 3 times a day. You know what I'm saying? Like if you think about the probability that your battery is going to last a certain amount of time, that's going to drop down, right? Does that make sense? Okay, we're going to go way too off on this. We'll revisit it. I'm not trying to dodge your like real world questions, but the real world questions are out there. There's application to it for sure, and that's what engineers do. One thing I've always said is that it's hard with math because in math we're trying to learn the skills, the mechanics, right? The mechanics of how we do math. At the end of the day, it's just a math course though, right? This is not an applied math course. This is not, you go to an engineering class and then you apply the math to something, right? That's where you apply it. But to do it, you have to be able to do the integral, right? You have to be able to do the actual mechanics. That's what this course is for. I wish we could turn this into a 6-hour credit and spend, an hour each week just doing application. I wish we could, but we don't, Okay, I will do some applications. I'm going to try and do some like center of mass stuff, maybe hydrostatic pressure. I don't know. We'll look at it. Work. We will talk about work to give you some use for this stuff. All right, let's do another one. That was 1 over x squared, right? That was 1 over x squared. How about 1 over x? Very similar function, wouldn't you say? 1 over x is very similar to 1 over x squared. They kind of do the same thing, don't they? In some sense. I'll show you the graph of this first. Here's 1 over x. And come on. And let me go back to this. This is the graph of 1 over x. Let me put 1 over x squared over here so you have it as a reference. So the purple one The purple one is 1 over x squared. The red one is 1 over x. I think we would agree that they're both behaving in a similar manner, right? They're both kind of diving down towards the x-axis. But the 1 over x squared seems to kind of head to that x-axis a lot faster than 1 over x does, right? But they both do have that asymptote. As you head out to infinity, they both head towards 0. So they both have the same horizontal asymptote. Is that going to impact the convergence or divergence? What do y'all think?
It'll probably
think-
still be convergent. It'll just probably have a little different area.
You think it'll be like bigger than 1 maybe?
Maybe.
Like- Okay, well, let's see. Let's see what the math tells us, all right?
That's,
so-
that's natural log, right?
The antiderivative will be. So I'm going to first set it up as a limit, right? I'm going to change the infinity to a t. Go 1 to t instead, 1 over x dx. Now I'm going to actually find the antiderivative, and I'm going to use the fundamental theorem of calculus for this. And that is the natural log. Now we're supposed to say natural log of absolute value of t. That's what we're technically supposed to do. But keep in mind here that t is going to infinity, right? From 1 to infinity, which means it'll never be negative, which means we don't have to worry about a negative being plugged into the log. So you don't actually need the absolute value because of where t is headed here. I'm going to leave it though. 1 to t. Oh, I'm sorry, that should be x. I apologize. That's x here. This is t up here. I got ahead of myself there. The antiderivative of 1 over x is natural log of x. And then we're going to evaluate it at t and at 1 and then subtract the 2. So this will be limit t goes to infinity. And then we will plug in. So when we plug in t, we get natural log. I'm just going to put t. And then minus natural log of 1. And the natural log of 1, I hope you all remember from the college algebra, is 0. And now I want to know what happens as I let t go to infinity for the natural log function. Where does it go? You have to remember what natural log looks like, right? This is what natural log looks like. And I'm trying to ask what happens when t goes to infinity on the natural log. So where does that function head as we go to the right forever?
Does it go to infinity?
Goes to infinity. It's very slow. The natural log function grows as you move from left to right. It grows. It doesn't grow real fast, but it does grow and it grows forever. So as you go to the right, the natural log function grows without bound. It just keeps getting bigger and bigger and bigger, which means that this goes to infinity, and infinity minus 0 is infinity, which means that this integral diverges. That means that it does not head to a number. 1 over x squared did, right? 1 over x didn't. It's like it was shrinking as you move from left to right. The 1 over x was shrinking, just like 1 over x squared did, but just not fast enough. It just wasn't fast enough. And I can hopefully convince you. What I'm going to do is I'm going to drag this point again. It's going to keep track of the area and watch what happens. Look at that. I'm already past 1. I'm at 3 now. I'm at 4 now. Okay.
Oh, if it's smaller.
Sorry.
It's decreasing at a lesser rate.
It is. It's getting bigger, right? This number is getting bigger, but not as fast. Like the further I go out, it's not getting big as fast. Yes. But I promise you that there's no number it doesn't go past. Okay, so let me go out. Like, give me a number that you think this never gets past.
5.
5. Okay, so what I'm going to do is I'm going to go out to 1,000. And let's see if I can bust out a 5. Oh, there we go. I busted out a 5. I'm out at 246. So then you say, okay, well, 5 wasn't ambitious enough.
Go to
How about
past 100.
50? You want to go 100?
Yeah.
Let me see, maybe I can get it here. Maybe I can get it in the first 1,000. I don't
Already
think,
past 100, bro.
no, we're looking at this number.
Oh, okay.
This number right here, which is, hold on, where's the label? Shit. Where's the label? Let me move that out a little bit. Whoa. Where's my label? Oh, here it is. There we go. Okay, so that way we can keep an eye on. So we said 100. Can I make this go past 100? Wow. Okay, so I'm at 1,000 and I'm not even past 7. So I'm gonna have to go out really big. Let's see if this computer can handle it. Didn't make it. I think we're gonna hit the limitation of the computer here. Undefined. Yeah, so I basically have gone past what this computer is capable of doing. All right. But I
Wow.
promise you, I can go far enough out to get past 100. Just the computer can't do it. But there is a number that I can go to. And there are ways to figure out what that number is, but we're not going to get into that here.
That's
Okay,
pretty
let's-
cool.
Yeah,
I
let's do,
I don't think I've ever seen Desmos just die like that.
yeah, it doesn't know what to do. Just, I mean, all of these programs have built-in precision values, like how many decimals they're willing to go out. I mean, it's not infinite. All machines have to have some terminal point or else they get caught in a loop. So that's kind of what happened there. It just didn't know what to do. So it just returned undefined, which is odd. Okay. You know what? Let's try this. Let's try this. I bet you I can tell you, I'm going way off topic. I'm so sorry. I bet you I can tell you where it is. Natural log of X. Let me graph natural log of X. All we have to do, look, all we have to do is solve this. I want to know when this gets bigger than 100, right? So I just want to know when natural log of T is bigger than 100. And that we can solve by doing E on both sides. So T bigger than E to the 100th power. So whatever E to the 100th power is, go that far out and the area will be bigger than 100. That's really far though. E to the 100th power is really far.
2.688 times 10 to the 43rd power.
Yeah, so so theoretically, right? Theoretically, yeah. Okay, let's look at another one. Okay, this one goes from negative infinity to positive infinity, right? So what I'm going to do first is I'm going to break it up. I'm going to go from negative infinity to, let's say, 0, okay, of 1 over 1 plus x squared dx, and then plus, and then I'm going to go from 0 to infinity of 1 over 1 plus x squared dx. I'm doing that because that's what I told you. If you go from negative infinity to infinity, you're going to go from negative infinity to any number you want, and then from that number to infinity. So I picked 0.
But we have,
We what?
no, never mind. I thought we had a hole at -1, but -1 squares. Wow, my bad.
Yeah, we don't have any discontinuities here, and none of the problems I give you right now are going to have discontinuities. So how do we do this? Well, the first one, right? This first one here, I have to set up a limit for. I have to do a limit. I need T to go to negative infinity, right? And I want to do the integral from T to 0 of 1 over 1 plus x squared dx. The second one, which I'm going to add, by the way, I'm going to add to that a second one, which is a different limit. And I'm not going to use T here because I don't want us to confuse the T from the first limit with this one. I'm just going to use a different letter. So I'm going to use R. let r go to infinity. And I'm going to go from 0 to r of 1 over 1 plus x squared dx. Do y'all understand why I'm using t and r? Just so I don't confuse two different letters in here and just keeping them as different variables. Is that all right with you? On the first
Good to me.
limit here, on the first limit, this is going to be limit t goes to negative infinity. And now I need the antiderivative. We all know the antiderivative of 1 over 1 plus x squared, right? We all know it. It's inverse tangent of x. We recognize that, formula 17. And we're going to evaluate that from t down here to 0. Or yeah, I like to say we're evaluating this from t to 0, like if we were moving left to right on a number line. Plus, now we have another limit. This time r is going to infinity. And for this limit, I'm doing, or for this one, it's the same antiderivative, inverse tangent of x. And we're going on this one from 0 to r. Questions? Limit t goes to negative infinity. All right, now let me plug in. I'm going to have two things subtracted here. So I first plug in 0, inverse tangent of 0. Then I plug in t, inverse tangent of t. I'll figure that out in a minute. Plus, now I have a second limit. Limit r goes to infinity. And my r's look terrible. R goes to infinity. And again, I'm going to have to do some subtraction here between two things. So first I plug in r, inverse tangent of r. And then I plug in 0, inverse tangent of 0. Now I've got to figure out what this is, right? So both of these have an inverse tangent of 0 in them, right? So just to
That's just
remind,
0.
yeah, just to remind you what this is what we're really saying when we say inverse tangent of 0 is equal to some value. Let's call that value v for value. Okay. What this really means is that when we take tangent of that value v, we should get 0, right? The inverse tangent of 0 equaling v means tangent of v equals 0. Meaning if I look at the tangent function, and we all know what the tangent function looks like, right? Looks like this. And it does it again, and it does it again, right? And this happens at negative pi over 2 and pi over 2, right? Isn't that where the vertical asymptotes are? We're asking ourselves, at what value do we get a 0 to come out? And that happens right here at 0. Now, it also happens over here and here. Why am I not looking over here and over here also for answers? Why not?
It's not in our domain.
Brandon, you went like that. Why? Why?
It's not in our domain.
Not in the domain. But when we say domain, we're talking about, remember, the original problem, the original idea here was coming from inverse tangent. And when you talk about inverse tangent, there is a domain restriction. You're only looking between negative pi over 2 and pi over 2. You're only looking at that one piece of tangent in the middle. So that's why my only answer is 0. So this is 0 and this is 0. Y'all okay with that so far? Now let me look at this blue one. Inverse tangent of t, but t is headed where?
Negative infinity.
Infinity. So this is really saying
That's got
wanna know what-
asymptotes.
inverse tangent of negative infinity. This is a weird idea, but what it really means is that tangent of some value v is negative infinity. Now, what we're saying is in the limit, what V value are you going to be approaching to get the tangent to spit out a negative infinity?
Negative pi over 2.
Negative pi over 2. Negative pi over 2. You can see it here. If you move along the tangent function, as you approach negative pi over 2, the tangent function dives down to negative infinity. Oops. Right? So this heads to negative pi over 2. Using the same principle on this one, that becomes tangent inverse of this time r is going to positive infinity, right? And that would be the other side, right? It goes to positive infinity over here at this asymptote. So this would be pi over 2 in the limit, right? You have to understand that this is a limit problem. So we're saying, of course, you can never plug infinity into anything. That's not what we're doing. We're saying tangent inverse of a number that gets bigger and bigger and bigger positive. That means that angle has to be getting closer and closer and closer to pi over 2. And from that, I can get my final answer. I need to move this down out of my way. So here's where we are. We've taken the limit. We've taken this limit. This piece gave us 0 minus, then we got negative pi over 2. Then plus, this gave us pi over 2 minus, and then this was 0. That double negative gives us a positive, right? So we get pi over 2 plus pi over 2, which is pi.
How can we see that graphically?
I'll show it to you. Okay, I'm gonna just save this. I don't even know what I want to call this. 6.6 improper infinite intervals. Okay, in case I need that later. So we were graphing the function f of x equals 1 over 1 plus x squared. There's the graph, okay? That is the graph of this function. I'm going to shrink down this axis. That's what it looks like, okay? Basically, this is what it looks like. And what we were doing was okay, what we were doing is we were basically going in both directions forever, right? And we were having we were trying to compute the area right here. And we're just going to let those 2 points drag out to in both directions, right? That's what we're doing. So I'm going to have the computer do this for us. I'm going to have it do the integral from negative m to m of 1 over, or do you know what? I can just do f of x dx. I don't know if y'all can see that, but that's the area right now. Can y'all see it? 2.38. Now I'm going to drag m. I'm going to go in both directions. Here we go. And watch this number. Watch what it gets closer to. .11, 3.1. Okay, 2. I've only got, let me go out to 10,000. So 3.14, 3.141, 3.1412, 3.413, 3.141. I need to go further. Should I keep going?
So it's correcting itself to pi.
Right.
It's approaching pi. It's approaching pi. In fact, check this shit out. If you wanted to get right now, if I just go and I I go to Wolfram Alpha and I type in pi, right? It's going to give me the decimal of pi, right? Oh, wow, it gave me a bunch of digits. 3.1415926, right? We could get these digits if we wanted to. We could. All we would have to do is just keep asking Desmos to go further. I mean, right now I've only gone out 100,000. We're at 3.1415726. So we've got the first 4 decimal point accuracy, right? We don't have the 5th decimal point. So I'd have to go further to get the 5th decimal. Let me go to 1,000,000. Hopefully we won't. I don't know what's going to happen here. Now, I'm just going to go, I think that's 100 million. Oh shit, it went undefined. What the hell? There we go. It's only going to let me go a certain amount. Okay, so 3.1415947. Yeah, so we only have 5 decimals and we had to go out 100 million. There's more accurate, there's more efficient ways to get decimals for pi, but this is one of them. And it's kind of mind-blowing if you think about it, because what we're really saying is this. If you wanted to, you're talking to your friends, I know when you talk to your friends, you're always talking about math and stuff. If you wanted to, if you could tell somebody that pi is equal to the integral from -infinity to infinity of 1/1 plus x squared dx. That is one way you could define pi if you wanted to. You could also define it to be the circumference of a circle divided by the diameter. That's another way, and probably a very simple way of defining pi.
A
Taking
much
the
easier
circle-
way of defining it.
Much easier way, yeah. But this doesn't give you any way to calculate it, does it? This doesn't actually give you a way to calculate the pi.
Yeah, unless you have a pre-measured out circumference and diameter, which
You would have to have some precision in measuring that, right? This we could theoretically do because we could change these numbers to anything we want, m here and m here. And once we pick these numbers and plug them in and do our definite integral, we'll get a numerical answer. And the bigger we let m be, the more precise it'll be. Okay.
you know what's funny about what you said of, oh, I know you always go talk to your friends about math, is I don't, except for when I'm drunk. I talk about math when I'm drunk for some reason.
Yeah, well, I'm gonna say I think I probably have done that myself many times.
I sometimes
I
find
used to
myself doing
drink a lot
problems
more
in
when
my
I was
sleep.
younger. I'm sorry.
I find myself doing problems in my sleep. Like before I wake up, I'm like, yeah, that goes like that. And then I'm like, wait a minute, what?
Yeah. Well, you know what? I didn't tell you all the story. You remember how we did the fundamental theorem of calculus last time, and I told you that the proof is beyond the class, like beyond the scope of this class. So the first time I ever proved that theorem, back when I was a student, when I was in school studying math, the internet was there, okay? So I'm not that old, but there wasn't like Google and YouTube and stuff like that the way it is now. So even if I wanted to go try and find a proof for it, it wasn't readily available to me. So we had to prove these, a lot of the proofs we did in school, we had to just figure them out on our own. And when I finally figured out how to prove it, it was something that I dreamed. So I'd been working on it for a while, and I finished actually, there was like one little step I was stuck on. And I don't know if I was like half awake, half asleep, but I woke up and I knew how to finish that step. I wrote it down on a whiteboard because I used to work on little whiteboards when I was at home, and I put it on a whiteboard. Anyway, I went to go visit my parents later that day, and I was all proud that I had finally proven the fundamental theorem of calculus. So I had the proof on the whiteboard in the back of my car. I went to my parents' house, and I opened up the back of my car to show my dad like what I had been working on. And their dog, they had a dog. It was like what was it? A Alaskan Malamute or something like that. he thinks I'm like taking him to the park for a run or something or to exercise. He comes running and jumps in the back of my car and just starts sitting on my whiteboard and shaking his tail and his ass on my whiteboard, and just like he races half the proof. And it was okay because I already knew how to do it in my head. You know, like I was already there, but it's just this story. I remember that dog had no idea that he was erasing this thing that I'd worked so hard for. But anyway, okay, what were we talking about? Yeah. Let's keep going. You want to try this one on your own? Why don't you see if you can at least get this set up? Okay, set up to the point where you get to that final step where it's time to do limits. You might struggle with the limits. Breakout rooms or no? Leave you alone? What do you want? No breakout rooms? Just let you go? Okay, I'm gonna let you go for a few minutes. Probably about 5 minutes. And on the poll, if you could just let me know if you get, I want to know when you're to the point where it's time to actually figure out the limits.
Professor, is it possible to already integrate and then break it out? Or do I have to break it out and then integrate?
It really doesn't matter when you do the integration. I mean, you're going to have to integrate no matter what, right? I'm going to leave this one right here. I'm going to paste the problem right there. That way, if you need to reference like how we broke things up, you know, you can. The notation that I use here is very important, you know, like breaking it into two limits. I mean, breaking two integrals, rewriting the integrals as limits. All this notation is important. All right, so just tell me yes on the poll when you get to the point where it's time to actually let t go to infinity or r go to whatever, however, whatever variables you use. Enjoy. Does anyone want to give the rest of the class a hint as to how you're going to find the antiderivative of that?
By parts?
Yeah, I did integration by parts.
Integration by parts. I'm going to start working it here in the background.
When do we say yes? Is that when we get to the point of doing the limit?
Yeah, if you get to the point of doing the limit, tell me yes. And hopefully you'll feel okay with it. You may or may not. We'll see when we get to it, or we'll work through it as a group.
I don't remember anything about he for limits.
What goes first, the top or the bottom?
Do you mean like when you're doing the subtracting?
Yeah,
It's the top minus the bottom.
Everyone take a look at what I've done up here. Make sure that you've gotten to at least that point, and if you have any questions, let me know. Notice how I did the integral on the side, right? Because I knew I was going to need to just figure out what it was with some integration by parts. Once I did that, then I just plugged that answer in over here. So does anyone have any questions as to where we are now? Split it up, limits on both, find the antiderivative, plug it in. You've got the 2 points we need to evaluate at. No? Okay, let me keep going. This is limit. T goes to negative infinity. And then in here, I'm going to have 2 sets of parentheses. Subtraction here. Okay, first we plug in 0. So 0 times e to the 0 minus e to the 0. Then I plug in t. So t e to the t minus e to the t. And then plus now another limit, r to infinity. Going to subtract 2 things here. Plug in r e to the r minus e to the r, and then the other one is 0 times e to the 0 minus e to the 0. Okay, this becomes -1 because e to the 0 is 1, right? So this right here, this becomes 0 times 1 minus this becomes 1. So that's just -1. And then over here on this one, we also have -1, right? So what we're left with are 2 limits that I think we're going to have to stop and talk about. So this first limit, I'm trying to take the limit as t goes to negative infinity of, and I'm only going to focus on this piece in here. I'm not going to look at the negative sign in front of it right now. I'm just going to look at this t e to the t minus e to the t. Oh boy. Okay, so how can I do this? If I let t go to negative infinity, here's what's going to happen. This is going to go to negative infinity times this. Okay, we have to be careful here. T is headed to negative infinity. So what does e to the t do when you go to negative infinity? We'll go look at the graph. What does e to the x look like? Well, e to the x looks like this, right? That's e to the x. So if I want to go to e to the negative infinity, I'm asking what happens as this thing, as you start moving along in this direction, where's this headed?
0.
To 0, right? So that's headed to 0. And then minus, now we already know, we just did this limit, right? So that's 0 again. Go with me? This here in green is a problem, okay? In Cal 1, you should have learned that if you ever take a limit and one thing is going to infinity and the other thing is headed to 0, that it's an indeterminate form. You can't tell me what that is. You cannot tell me that that's 0. You cannot tell me that that's infinity. All you can tell me is you don't know what it is yet. So what I'm going to do now, because I know this goes to 0, there's no problem with this, right? That's not an issue. That just goes to 0. The real focus of my attention right now is this. What is the limit as t goes to negative infinity of t e to the t? That's what I'm trying to figure out. I already know it goes to negative infinity times 0, which is bad, right? And my Cal 1 students, you don't know, that's what I always like to say. That's a bad situation, right? So we need to do something. Any of my Cal 1 students remember what to do? Or am I going to cry right now? Am I going to cry? What do you do when you have 0 times infinity? Anybody? I don't care.
Gotta derive.
Do what?
You gotta find the derivative of both. Well, L'Hopital.
Well, we will do the derivative of both, but you can't do it yet. L'Hopital's rule only works when you have infinity over infinity or 0 over 0, which we do not have.
You gotta rearrange it to God.
We take the natural log of it.
Nope, no natural log on this. You have to rearrange it. You have to, anytime you have 0 times infinity, you have to pick one of them and drop it to the bottom. Okay, so watch, this is what I mean. I'm going to rewrite this. I'm going to leave the t on top, and I'm going to drop the e to the t on the bottom as e to the negative t. This is just rewriting it algebraically, right? T on top, e to the t is the same as writing e to the negative t on the bottom, which seems strange, but watch what happens when you do this. If you let t go to negative infinity, this goes to negative infinity, doesn't it? Still. But now if I be real careful, if I let t go to negative infinity, I'm going to have e to the negative infinity. What's negative infinity?
Infinity.
Positive infinity. So
Yeah.
what does the bottom do? Well, you go back to this graph, and now instead you're moving out to the right to positive infinity, and the graph goes where?
Infinity.
Infinity. So now you have something like this, infinity on the top and infinity on the bottom. It doesn't even matter that one of them's negative and one of them's positive. So the top is headed to something infinite, the bottom is headed to something infinite, and now at this point, L'Hopital. So this is this. So now L'Hopital, now different people do it different ways. I think the book puts an H over the equal sign to let you know they're using L'Hopital's rule. In my class, and my students know that I like to put an L with a circle around it. It doesn't matter. You can put an L, H, something to let people know you're using L'Hopital's rule. And L'Hopital's rule says that once you're at Once you have infinity over infinity or 0 over 0, you can then take the derivative of the top and bottom separately. So the derivative of the top is 1, and the derivative of the bottom, be careful, is negative e to the negative t, because you have chain rule. The derivative of e to the t is itself, times the derivative of what's up here, which is -1, which is why I get a negative to pop out in front. Now we look at this limit. The top goes to 1. The bottom goes to, let's see, check it again. You got to be careful here. We're letting t go to negative infinity. Negative infinity is positive infinity. So e to the positive infinity is infinity. And then negative. So the bottom is headed to negative infinity. Where does that go?
0.
0. Why? Because we have a fixed number on top, 1, and we have the bottom that gets bigger. It doesn't matter, it's getting bigger or negative. It's just a huge number on the bottom, fixed number on top. That ratio vanishes to 0. So all that work to determine that this first piece right here goes to 0. On an exam, which is next week, if you do this, if you do a problem like this, and you tell me that this goes to 0 without any supporting evidence, I won't give you credit for it. All right. Because in my mind, you're just guessing. All right. You're just guessing that that's 0 and you got lucky. It doesn't have to be 0. 0 times infinity does not have to be 0. I mean, there's limits where 0 times infinity turns out to be e. Okay. So, I mean, it just every problem is different. All right, we're not done. We still have to do this one over here. The one here in blue. We got to do that limit as well. We having fun yet? Limit r goes to positive infinity of r e to the r minus e to the r. Okay, so now what we do is,
Okay.
Pardon?
Okay, we're gonna do this again. Yeah. But like, we know it's 0, so can we say it's 0 then?
This isn't the same limit. Because this one, t was going to negative infinity. Here, this one, r is going to positive infinity, right? So we aren't necessarily going to get the same answer. So let's just check to see what happens. If r goes to infinity, this is infinity, right? Times, now e to the infinity is what?
Infinity.
Infinity. So that's infinity. See, I don't have 0 times infinity now. I have infinity times infinity. Infinity times infinity is infinitely big. So that's not a problem. I know this is getting huge. But then I'm doing what? Subtracting from it. What is this?
Infinity.
Infinity. And infinity minus infinity is an indeterminate form. It's not 0. So how do we deal with infinity minus infinity? Remember how to deal with that?
Would it factor out e to the r?
You try and factor. Exactly. You try and factor. So I'm going to try and factor. I can pull an e to the r out of both of these. Right? They both have an e to the r. So I can pull an e to the r out. And now let me just check it again. What happens is I let r go to infinity. This goes to infinity times, now here, this is going to become infinity minus 1, which is infinity, right? And now we have infinity times infinity, not infinity minus infinity, infinity times infinity. And infinity times infinity is infinity. Which means that this becomes infinite. This is -1 minus 0 plus infinity minus -1 plus 1, which means that this thing
It goes to infinity, doesn't it?
it does go to infinity, which means the integral
It's there's a word.
Diverges.
Diverges, yes.
It diverges.
My brain was trying to go to indeterminate and
Yeah,
I knew
yeah.
that wasn't right.
All that work to determine that the integral diverges.
So on one of these, does the actual numerical answer matter, or is it diverges versus converges? Like,
If it's convergent, then your answer should be a number.
okay, if it
it's
diverges,
infinity
though
or
it's
something else, it's divergent.
okay. So it doesn't matter. It's infinity diverges.
Diverges, exactly. If it's not a fixed constant, it's divergent. That's a good problem. So again, I will invite everyone who is unsure about L'Hopital, or just it's been a while since you've done limits like that. What I would expect from a Cal 2 student is that you understand all the indeterminate forms. So this is what I give my Cal 1 students. I give them a page that shows all the different indeterminate forms. Anytime you have 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0. All of these are what we call indeterminate forms, and there's methods for going after each one of those. So you should be familiar with all of this stuff, or you could get caught in the middle of an integral problem. You could get caught on the limit part and not know what to do. So yeah.
That would be a shame.
Yeah, and that's why we do it in Cal 1, because later on it comes up, right? Okay, let's see.
Glad to see it's coming up again. It's one of those neat things that Cal 2 especially is bringing back stuff from Cal 1 and earlier stuff that I never thought I'd see again.
Those limits, the fundamental idea of trying to figure out how numbers are interacting with each other when something goes to infinity, something goes to 0, that's something that just stays within engineering, physics, chemistry. It's, computer science. You've got these competing things. Something gets big, something gets small. What's happening? What's happening, right?
Is that
Right, the last
limit summary allowed on the test?
For my Cal 1 students, yes.
Okay, but not for us.
Yeah, for you, I would expect that you know how to handle that.
Gotcha.
I've had those lumped in with my notes this whole time.
Yeah.
I'm using my same sheet of formulas from Cal 1 because it's the same.
The important thing to note about that sheet is that even though I give my students this sheet, it doesn't tell you what to do. It just tells you what's indeterminate. So like if I'll just briefly summarize this. If you have one of these two forms in a limit, then you go straight to L'Hopital, because L'Hopital says you take derivative of the top and bottom. That's it. So if you have those two, you go straight to L'Hopital. If you have this, you do what we just did. You take one and drop it to the bottom and then use L'Hopital. If you have this, you factor like we just did. These I haven't even talked about. All three of those require that you bring a natural log in, and those are complicated. Let's see, I don't think I have any examples that are going to use that, but not to say that it won't come up. Let's look at this. This is, I talked to you all last time about, probability distribution functions, and the area under them has to be 1. This is the most famous probability density function that exists. This is your bell curve. This is a function, okay? The variable in here is X. Everything else here is a number. Sigma, mu, those are all numbers. The mu is the average, and then the sigma is the standard deviation. So if I plug in numbers for mu and sigma, I'm basically going to have an exponential function that looks like this. Okay? That's what the standard normal distribution looks like. And if I change the values of mu and sigma, it changes the shape of the graph, your bell curve, your normal distribution, it changes it. But the important thing is that the total area under this is 1. Okay, it converges to 1. Now, I will tell you right now that if you tried to do the integral on this, okay, negative infinity to infinity, of that function, okay, if you tried, you would not be able to integrate that. You would not be able to find the antiderivative. Okay, you can't. You can't, I can't. Okay, it's not possible. It's not possible to find the antiderivative of that by hand with any method that we know. We can do it with series, which is chapter 8. So that's why series are important, because, well, there's a lot of things we can't integrate by hand. Okay, so series are going to allow us to do that.
What is it that throws this one off?
There's just no technique. I can give you a simpler version of this. If I just ask you for the antiderivative of e to the x squared, there's nothing you're gonna be able to do.
Okay, it's
That's a
that
very-
e to the x with the extra stuff up there.
It's the x
That-
squared. We can do this. We know the antiderivative of e to the x. It's just itself, right?
It's that x being overly complicated that's throwing us off.
It's the fact that it's squared.
Oh, okay, it's the square.
Okay. The sigma and all that doesn't matter. This is a constant. You can pull that out of the integral.
Yeah,
You know, I mean, this is a constant. That's a
It's-
constant. It's really, at the end of the day, just an x squared up there, and that, you know, nothing you have is going to work, right? No, nothing in our bag of tricks. No integration by parts. No partial fractions aren't really applicable here. There's just nothing you can do, all right?
you can't use sub it either, huh?
You can't do u sub because the derivative of x squared is not there. And even if you try and make it appear, it's not gonna help. Okay. A nice formula. Okay, so this, I'm not gonna prove this because we only have 10 minutes. If we had time, I would prove it. If you ever do an integral from an improper integral from 1 to infinity, it's important that we do 1 to infinity, all right? And not negative infinity to infinity. If we're going from 1 to infinity of 1 over x to the p, so p is the power, okay? P is the power we have on the x. That x is in the denominator. The conclusion is that it will diverge if p is less than or equal to 1, and it will converge if p is greater than 1. So when we did this problem to start class, right? Remember we started with this one? We got an answer here, right? I think it was 1. But the big thing was it was convergent. I'm just going to put C for convergent. When we did this problem, 1 to infinity, and we did 1 over x, we got that it was divergent. I'll put div, divergent, convergent, all right? When you look at it this way, this power here, that power right there is 2. This power here is 1. This corresponds to this, and this corresponds to that. If the power down there is bigger than 1, you're going to get convergence. And if the power there is less than or equal to 1, you're going to get divergence. Please remember that. Okay, it'll be useful down the road. I'll give you one more example. Let's say we had integral 1 over square root of x dx, and we're going from 1 to infinity. Just tell me whether or not that converges or diverges.
Wouldn't that diverge?
Why?
Because that's x to the power of 1/2, which is less than 1.
X to the power of a half, right? The square root means 1/2 power. So 1/2 is less than 1, so it's divergent. So this will diverge. Whereas if I did this, 1 over the square root of x cubed, that didn't come out very good, x cubed dx. Now you could look at this as being x to the 3/2 power, right? That's what that really is. And 3/2 is bigger than 1, which would mean we have convergence. Now, I'm not, for this one, I'm not telling you what the answer is. I'm just telling you, I know right now it's going to converge. Okay, I'd have to go work it out to tell you what it converges to, but I know it converges.
But you can negate a decent portion if you just, oh, wow, look, it diverges.
Absolutely, because if it diverges, you don't have to do any work, right? You're done. All right, and that takes us to the next topic, which we won't talk about right now. I think you've got enough on your plate.
What do we got for homework for this?
Yeah, let me get in there and take a look at where the split in the problems is. So I tell you do 1 through 31 odd, but that won't apply. Wait a minute, 6.6. So you should be okay with this up to 21. So 1 through 21 odd. Let me just look at those again. Yeah. And then the rest of them will be after next class. You'll be able to handle the rest. Let me see what else.
The exam's next Wednesday?
Wednesday, yeah.
Gotcha.
Yeah, if I go to my YouTube channel, let me go to Cal 1. You see, I have a lot of different, I don't like my class videos for those. What else do I have? Can I search my playlist?
It's really funny seeing my YouTube feed full of your math videos.
My sister said the same thing. Like, go to YouTube, it's all math. No entertainment. It's math.
Hold on, I want to find the playlist. Where's the thing for all my playlists? I thought there was a thing I could click on for all my playlists. Okay, spring 2019. Let me just see. I'm just trying to go back and just find some random video here.
But I was looking at our schedule.
General.
This is f of c, the function at
Maximum.
some value c is called.
Ooh, this looks like it.
Indeterminate form that we ever.
Here we go. There we go. That's me talking about right there.
And creation of this.
L'Hopital's rule. Let me see. Go through here.
Let's clean this up algebraically.
Infinity over infinity. So let's see. I will. Why don't I share this playlist on the chat? Okay.
I mean, it's
And
not
then
like-
it looks like day 14. I cover it. Let's see if day 15, if I'm doing it still. Come on, man. This is just one of my old Cal 1 classes. So you're free. Yeah, this is more. So it looks like day 15, I'm still doing L'Hopital.
f of
Yeah, so all of 14 and half of 15. How do I share this thing?
We're at that point.
There it is. Share. I want to share the playlist though.
Should just be the link at the top will get you the playlist,
Unclear.
the URL.
There we go. Okay, in the chat.
All right. We have couple of more things to define, and then we'll.
God, that guy sounds like an idiot, doesn't he?
Main idea.
Yeah, gee.
Something called.
All right, there we go. Okay, I sent the link to that playlist, and again, it was day 14, but you know, I have videos going back 2013, 12, 10. I mean, you can go search my channel for 2413 and find another playlist. Sometimes, you know, I had better semesters than others. Sometimes it goes better, you know, so I just went and picked a random one there. That's, again, this is if you feel like L'Hopital is something that you feel real unsure about, you know. But otherwise, I mean, I think that's it. I think you should take the weekend, make sure you do the homework on 6.6. Take a look at the review. I mean, really, when it comes down to it on the exam, big picture is that I want to make sure you know how to do trig sub, right? You got to be able to do trig sub. And in that trig sub, there's 3 different types, right? I may not be able to test you on all of them because it might just take too much time. but you should know how to do trig sub. We know that when we do trig sub, a lot of times that winds up requiring us to do a trig integral, which like sines and cosines or, you know, things like that, or tangents and secants. So I a lot of times like to have almost all my tests that I've ever given have always had somewhere in there, you have to do like an integral with like cosine squared. So that way you show me that you can do the power reducing formula on the cosine squared. And then also that you'll eventually have to, you know, draw your reference triangle and do, you know, do your whatever to figure out what you're trying to figure out. But I also like to have theta appear in there so that you have to solve for theta, not sine theta or cosine theta, but theta itself. And then I wouldn't be surprised if somewhere you have to complete the square, but that could come in different places. I mean, when we get to, remember that important day we had where I said, here are all the things we should know how to do before we do partial fractions. Right, and it was like constant over linear repeated, right? Linear over quadratic irreducible. And then I showed you the way that I like to do that one type of problem where I was like, this is the way I do it. You know, you might see it a different way from a tutor. I mean, that's usually on a test. Let me see. Let me look at this review. I just don't want you to think that this review is like, okay, if I can do the review, I'm good. If you can do the review, yes, good for you. But that doesn't mean you're necessarily prepared for the exam because, you know, okay, this is trig sub. There's no surprises here. This one, partial fractions, you got to have long division first, right? That's your first step. Another partial fraction, long division, and it's a definite integral. So at the end, you got to plug in numbers. Improper.
I think we just did that one actually.
Well, we went from negative infinity to infinity. And remember on ours, we had a problem with the side that was going to infinity, didn't we? That's
Yeah.
where we had a problem. When we did ours, right here, this part, the part that went to infinity was the part that blew up and got huge. This part wasn't a problem.
Yeah, so it'll probably be some like actual reasonable number, but the derivative is the same.
The
But we'd
anti-derivative.
also break that up. Like,
Yeah,
wouldn't we break that up into like a negative infinity to 0 and then 0 to 2, or would we just do?
No, because it doesn't go to infinity, you can just go from like t to 2.
Gotcha. Okay.
Yeah. Yeah, and I said skip 5. This is a good one. This is partial fractions improper. So you've got an improper integral. You got to go from 0 to infinity. So you got a limit, right? But the integral itself is a partial fraction problem. So there's a lot going on here. You got to figure out a way to, these are both irreducible quadratics. So you got to do your partial fractions and rewrite this. Well,
Get a nice ax plus b over it, and
over x squared plus
cx
1.
plus d. Ugh.
Yeah, solve the system. Nowhere on this do I see a completing of the square. Nowhere on this. If you got to go, you can go. We're at it. We're done. But here's another review that I had 3 reviews I could have given you. I only gave you 1. Here's one. Okay, so there's a perfect example. Linear over irreducible quadratic. That's where I showed you like the way I like to do it. I try and make the top look like the derivative of the bottom. So that was on a test. If my point again is, if you do this review and you're like, I've got it, and then you get this problem, well, to me, this is fair game. I mean, we did problems like this. So I don't want you to focus too much of your attention just on the review. That's pretty similar, right? That's partial fractions. Another partial fractions, long division first. Another partial fractions.
This is the
Oh.
partial fraction test.
Wait, on this one, yeah, this, what the hell? This just, okay, so this is just a definite integral. There's no problems. It's not improper. So this one is just this is a definite integral. So, you know, can you find the antiderivative of that? That's not really that bad.
It'd be integrate by parts on that one, right?
Probably a parts.
Yeah,
You-
because that natural log is nasty.
Yeah, you probably let that be you. And then everything will work out nice. Let's see, I'll just show you the third one I have here. Oh, look at this one. This one was a trig sub, but you can't have the 9 there.
So you got to factor out the 9.
You got to pull the 9 out,
Oh, by 4, no.
right? You got to pull the 9 out. So the 9 comes out as a 3 on the bottom, so 1/3. And then this becomes 4/9 minus x squared. Then you do your trig sub. This one, pretty clean trig sub, just, see what it turns out to be. Ah, there it is again, linear over irreducible quadratic. Long
So,
division.
With the trig
long
sub,
division.
there was a piece you had that we were allowed to print out to take onto the exam, right?
Yes.
And it was,
Should
and
do.
I've just been using the page in the book that has that for my homework,
you-
but I
you have to be
can't take the
careful.
book,
Yeah, you
Yeah.
have to be careful because what I provide you, you need to make sure that you understand on the trig integrals sheet that I'm allowing you to have on the test. It tells you what trig sub to use.
That's that little box down at the bottom, that's in the book and that's what I've been using. So I've been having to manually work out what
These are.
those are,
Yeah, that's right.
because you said that wasn't going to be something we could have on the test. So I've been trying to do it manually and then try to get where I just associate them together, which that's harder.
The way I think about it is this. If I'm gonna make a trig sub of sine, right? Just think that it's sine. In here, I'm gonna get something like, this is gonna look like 1 minus sine squared. And 1 minus sine squared is cosine squared. So this is all gonna turn into cosine. A cosine theta. Excuse me. And then here I have tangent. So if I plug in tangent here, I'm gonna get something that looks like 1 plus tangent squared. But 1 plus tangent squared is secant squared. So this is square root of secant squared, so that's just secant. So this will be a secant. And then here, if I plug in secant into this, I'm gonna get something, sorry, right here, then I'm gonna get something that looks like secant squared minus 1, which is tangent. So this turns into a tangent. But I mean, that's just kind of a very like step back way of thinking about it. But if you just have to plug it in and grind it out, plug it in and grind it out.
The funny thing is the a squared plus x squared is the one that I have best, and I just remember what they are
Yeah, that's
because
fine.
it was one that I had that one enough that I don't know why, but that one in my brain, it's the derivative is the a secant squared, and then the whole thing turns into the a secant.
Gotcha.
And I don't know why that one associated well. The others, I'm gonna have to work them out.
Yeah. All right, I've got to run to my office hours. Are there any questions? You'll have an opportunity on Monday to ask anything else about the test if you'd like. But have a good weekend.
You too. Thank you, sir.
All right.